The IOWN APN is a novel and innovative optical network which achieves high capacity and low latency with low power consumption. The APN realizes low latency, high capacity, on-demand services by providing end-to-end optical connections between any 2 points. However, optical paths should satisfy several constraints which arise due to network facilities and the amount of communication traffic. Therefore, the APN requires a mechanism to flexibly control a large number of optical paths. The system that achieves this is the Photonic Exchange. This diagram shows the mechanism of optical transmission. An optical signal is transmitted with a single wavelength assigned to it from the start point to the end point. By assigning different wavelengths, multiple optical signals can be transmitted simultaneously. A range of wavelengths with close optical properties is called a wavelength band. In conventional optical transmission, single-band transmission using a single wavelength band, such as C-band or L-band, is common. In contrast, the APN uses the Photonic Exchange to enable multi-band transmission, a technique which uses multiple wavelength bands to achieve high capacity. The Photonic Exchange performs 3 functions to take advantage of multi-band transmission: interband wavelength conversion function, wavelength conversion function, and channel power pre-equalization and multi-band transmission function. Let me explain the interband wavelength conversion function. This is a case where signals are sent from the optical transmission device on the left to the one on the right. When an optical signal was wavelength converted using conventional technology, the optical signal is converted to an electric signal. The signal is processed electrically and then converted back to an optical signal for transmission. Therefore, power consumption and latency are key issues in conventional wavelength conversion systems. The Photonic Exchange has solved this problem by performing wavelength conversion of optical signals directly, without conversion to electricity, by applying a PPLN, a cutting-edge device currently under development by NTT Science and Core Technology Laboratory Group. This is the world's first system equipped with an interband wavelength conversion function, which can simultaneously convert multiple WDM channels in one wavelength band to another. Even when optical signals should be transmitted on different types of optical fibers, the system can flexibly apply the optical wavelength band according to the optical fiber type. Let me explain wavelength conversion function. Operators A and B, respectively, have optical paths as shown here. Suppose we want to set up 2 new optical paths from operator A to operator B. We first try to select wavelengths 1 and 3, which are not in use in operator A's network. However, in operator B's network, wavelengths 1 and 3 are already in use. So optical paths cannot be set up between operators A and B using wavelengths 1 and 3. To set up optical paths in this situation, the wavelength conversion function is used to convert one wavelength to another. First, wavelength 1 is converted to wavelength 2, which is not in use in operator B's network. This fills up operator B's C-band. So wavelength 3 is converted to wavelength 6 in L-band. In this way, end-to-end direct optical paths can be efficiently established even if wavelength conversion needs to be performed across wavelength bands. Let me explain channel power pre-equalization in multiband transmission. In multiband transmission, the nonlinear optical effect causes optical power to transfer from shorter wavelength signals to longer wavelength signals. As a result, shorter wavelength signals fade, becoming underpowered at the receiving end, making long-haul transmission difficult. To solve this, optical power tilt control is applied at the transmitting end. The tilt control eliminates the problem of lack of power at the receiving end. With conventional technology, an additional device has been needed to generate the tilt. In contrast, with the Photonic Exchange, a stable power tilt can be applied without the need for an additional device. Moreover, the Photonic Exchange calculates the optimum tilt to avoid undesirable power transition. Because of these features, the Photonic Exchange achieves high capacity with lower power consumption compared to conventional systems. The Photonic Exchange, which enables high-capacity, low-latency, low-power optical communication, complies with the Open APN functional architecture defined by the IOWN Global Forum. Going forward, we will proceed with its social implementation and contribute to the wide deployment of the APN.